and also give a sort of review of optimal control. Now I know many of you have never had optimal control, but the concepts that I want to teach you about are so simple you can explain them today, just like that. I mean, how many of you have seen Bellman's principle of optimality? Anybody? You have. Anybody else know Bellman? You've heard of Bellman, right? No? But anyway, it's so easy described. So what's the optimal route to get to Naran over there? Is it this way? I think it's pretty clear. If I want to minimize making a fool of myself and time, I would walk over like this. Okay, now a question, everybody. What's the optimal route to get from here to Naran? I just told you. So that's Bellman's principle of optimality. That basically, if I know the optimal path from here to here, and then I ask you, well, what about starting from there along that route? Well, you just keep doing what you were doing. So Bellman's principle of optimality, there I explained it, it's optimal control. And that leads to algorithms and all sorts of equations and stuff. So I'm actually going to explain that in deterministic terms and explain to you how it's identical for stochastic systems. And that's what's really kind of cool about stochastic control is it's not that different than deterministic. And my own feeling is the only reason for teaching it, stochastic control is only useful because it brings in so many more tools for approximation and insight and all of that. Most systems you can pretend they're deterministic and get a really good solution. That's true in mechanical engineering examples most of the time. It's not true in finance. So in finance, the volatility overwhelms everything, and so their deterministic model just doesn't make any sense. It's one of the only examples I can think of. Probably in biology there are examples as well where stochasticity is so dominant that you really have to think about the noise. All right, so where were we? Let's go look at this linear control problem. Okay, so I'm still, fixing. I mean, this is like a survey of the course. So, basically, I'm going to go in way more depth later in the semester. But we have this linear state space model. And so I think I might have used T before, but anyway. And so I've got now an m-dimensional input. Before, in the very beginning, there was no input to the system. And I've got a matrix here of the right dimensions. So A could be an m by m matrix, n by n. And for this to be a controlled Markov model, this noise here, disturbance here, has to be IID. Independent and identically distributed. So a sequence of independent draws of, say, a Gaussian random vector, or it doesn't have to be. It could be, its entries could be uniform. It could be exponential, anything. Cauchy. I need a second moment, as we'll see. Not Cauchy. And the typical thing you get in a stochastic control course is looking at quadratic cost. Okay, so why do people impose quadratic cost? They'll say it's energy. Well, they're full of it. It's because you can compute things. You know, it's the only reason we always impose quadratic cost, is because we can compute things like that. There are very, very few cases where it really makes sense to look at quadratic cost. It's, you know, for computation. So in a linear system and quadratic cost, everything becomes easy. And so basically, I mean, I guess you haven't, but some of you have seen the case where the noise is 0. So okay, so if so what happens if the covariance is 0? That means there is no noise, right? So we're just looking at a system with just the input is affecting the state, plus the state dynamics here. And the typical thing you look at in a, you know, first-year graduate control course is you look at this value function. Oops, I forgot the minimum. Okay, so by writing minimum of a u in this abstract way, I mean I'm taking the minimum of all sequences of inputs. And here I'm looking at the sum, the total cost over the entire time horizon. And so this is a quadratic function of x and u. And so for this to be finite, then, and given the fact that r is positive, the input's going to have to go to 0. You know, and you know, I mean, the state might not go to 0 if depending on assumptions on q, but assumptions are usually imposed that say that x has to go to 0 as well. This is what's called an observability property that implies that x has to go to 0 as well. So basically, we're trying to drive the system to 0. So 0 is our Naren sitting here. I'm harassing Naren because he's not taking the course. He should be. Just kidding. All right. So what's Bellman's principle of optimality here? Is that if I've found that minimum, and I'm sitting here at time 0, and I'm at state x, and then after one step, I'm here, you know, then I know the remainder of the, you know, what to do next. And that Bellman's principle of optimality tells us, well, right here, that here I'm minimizing, I'll write it like this to be explicit. So I'll also write u 0 to infinity to emphasize I'm looking at sequences from 0 to infinity. I can get a fixed point equation. So this whole minimum, which is an infinite dimensional problem, minimizing over sequences, it's the minimum of the first step cost, and that actually appears here, right? When n equals 0, x0 equals x, and I've got a u0 here, and that's what this is. And then plus, you know, remember I just took that hop, plus the cost from where I hopped to onwards, which is just j star of x1, right? And that's, let's make this a bit more explicit. x1 is just ax plus bu. Okay, so again, this is what if the noise is 0? What can we do? So this is called the Bellman equation. And it's a fixed point equation in this function j star. And all the optimal control problems you end up with fixed point equations of this form, where you've got like a J star sitting here, and then a minimum with J star on the right-hand side as well. And you'd like to solve that equation. And in this particular case, you can solve it. J star is quadratic. I might, it's a homework problem, make you create the Riccati equation later on when we get to that part of the course. And the minimizer here gives you the optimal control. So the optimal control is state feedback, you know. So U star is some function of x, right? When I perform this minimization here, you know. And just by construction, you know it's the first control action I'm going to apply. So when I'm in state x, I'm going to minimize this to figure out which action input to apply at time 0. And that's a state feedback policy. All right? And it turns out it's just equal to some gain times x. So it's linear state feedback. Right, so that's why people love linear systems. Everything just comes out like that, you know. And Kalman, you know, who developed all this stuff, was here most of the time when he was doing that. It's amazing. I didn't know that, by the way. You know, and not until I interviewed here did I realize how much work Kalman did in Gainesville, right here. And the thing is that this is trivial. You know, writing this down, you applying Bellman's principle, guessing this is a quadratic and verifying it's true, blah blah blah. Anybody at the time, it was like a I don't know, an elementary school project. But showing that this Riccati equation has a nice solution, showing that xn does go to 0 under some observability properties of Q, and all the beautiful structure he got of the optimal control solution after that. There's also some passivity results he got for the optimal solution. It's breathtakingly beautiful. I mean, he just did amazing, amazing things. So just thank you, Kalman. He was a difficult person, apparently. Apparently his personality was quite strong, but he really did some incredible things. And of course, not alone. Yep.
So,
yeah.
From the principle of optimality, I'm trying to understand why it's a fixed point equation.
Yeah.
Actually, I can kind of see why.
Well, that's just a definition of fixed point equation, right?
So,
I mean,
so like, it's hard for me to see that. So when I think of it, it would just be like x equals t times x. If you put x into like the transformation, you get back x. Is that? Oh, am I incorrect? Or is that?
Well, I've got a mapping of functions, and it maps to itself.
Okay, and
yeah.
I can conceptually see that from the principle of optimality.
Oh, no, but, well, first of all, this is conceptually, I think it's clear from my hop. This is like a one-liner from the hop that I described. And then what's your question?
Well, it's just at first it was hard for me to see why that's a fixed point.
Oh, I'm just defining that to be a fixed point equation. So I have this I define as an operator on functions. You know, give me any function j, I get a new function j prime. Yeah, yeah. And so the fact that I actually end up with the same function makes it a fixed point equation. Okay. Yeah. Okay, cool. So now, what about it not 0? What happens then? Okay, so again, what would you do? So you'll see, this is going to be fun. So you obviously not, I mean, maybe it's obvious, maybe not. Is it obvious you're not going to do something like this? If there's noise. I mean, take a look. I mean, every single time you're hitting xn by noise. And I'm assuming this noise is IID, it's not going away. And so I'm basically summing noise, you know, and the cost is quadratic, so it's positive. So I'm squaring that noise. So I take expectations. It's not going to help us any. So you're not going to look at total cost in a stochastic setting. So what people do is they look at the average cost case. K using n. So, all right, so what am I doing? What are the differences? First of all, I'm averaging, so that's different than looking at the total cost. I emphasize in here that for any initial condition, just like there I had an initial condition and then I looked at the value, here though I'm saying, well, I don't have an x on the left-hand side, and that's because there won't be. You know, it's really hard to find examples where this average depends on the initial condition. So usually it doesn't depend on the initial condition. Unlike this, where of course it does. Here, if I start at 0, I can just stay at 0, and the cost is 0. You know? So those are the things. So this minimum, of course, is under restrictions. I mean, you've got to be much more careful with the stochastic case. So I'm going to assume my u is going to be the admissible u's. It's going to be I'm only allowing functions of this form. Right. I could be much more cavalier in deterministic settings. You know, it doesn't make any difference. But here, I've got to make sure that I impose causality. So if I could predict the future, I could cancel out the noise, perhaps, and get 0 cost. But I'm causal. I can't predict the future. So what do you think happens? Well, you've got to write down a Bellman equation. And there is one, and I cannot possibly motivate it today, but I will motivate it as time goes on. You notice I'm being very careful not to erase this. So let's see, what was our Bellman equation? It looked like this. Well, it's identical. I've got J star, I'm going to call it 8 star of x. That's one difference. And I've got, that's going to be random if x1 is stochastic, so I got to take expectations. And something else is missing. Well, first of all, so this would be like the Bellman equation. Notice that this fixed point equation is not unique because I could always add a constant to J star and to have a new solution. We get uniqueness through a boundary condition, and that boundary condition here is the fact that J star of 0 equals 0. So that's how we get a unique solution here. Similarly, if I have an expectation, the same thing is true. I could add 12 to both sides, I get a new solution. Okay? But this is not the Bellman equation, actually, it turns out. Because if this equation held, then it would turn out that this average cost would be 0. So what's missing is I left out a term. So the Bellman equation for the average cost problem is basically almost identical to the deterministic problem with 2 changes. I stuck in a conditional expectation here, and I added on a constant. That's all it is. And what's the solution? Nothing changes. Noise doesn't change the solution at all. You get u equals k star x. Yeah.
Is this the same?
What's that?
The eta star is the same.
Yes, that's right. Yeah. So it turns out that 8 star is J star. Is the unique solution that's 0 at 0. Well, you also have to have growth conditions as well. So first of all, it's 0 at 0, and it has quadratic growth. It doesn't blow like e to the x squared or something. I mean, you can get crazy things happening, you know. Well, anyway, I'm going to leave those technicalities out. But it's basically the unique solution, such that this is 8 star 0, and also you get the exact same feedback laws. So noise has no impact on my policy. It's irrelevant. And you know, it doesn't. You could have some crazy statistics of n. The only thing we need is a finite variance. That's all we need. You know, this could be a really strange noise, but my policy would not change at all. My performance would. So this is very sensitive to the noise. So eta star is sensitive to the noise or disturbance. And the policy all right, so this has always been considered just like a freak of nature, just a one-off thing. But I want to try to argue that for many, many, many...
I can learn to understand you much better if I can get familiar with the way you talk.
Okay.
I need your permission to help.
Sure. I love it. Yes. Okay, so...
Grab your voice, I'm sorry.
In this case, you know, I mean, people thought just, you know, it's some freaky thing about the linear quadratic nature. But it turns out that one of the themes in the course, I want to show you, this is sort of a general principle. So they're not equal in more general control problems. But the total cost problem in the deterministic setting and the average cost problem in the stochastic setting are very often closely related. All right, and I'll actually try to make that clear. And that's a really useful fact for people who are trying to do approximate dynamic programming, because you can take a simpler deterministic problem where there's no noise at all, maybe not solve it like we did here, but get some good understanding of the deterministic system, and then use that as an architecture for approximate dynamic programming for the stochastic model. And that's something that's going to be a theme, one of the themes in the course. Cool. So this is like, I don't know, sometimes I call this an ODE, an example of an ODE method or mean dynamics. You know, it's so funny, principle, how about that? I'll make it really pretentious. It's not a principle because it's, you know, not totally generalizable, but it's a good hack in a lot of cases. So let me give an example of that. Okay, cool. So let me give the most. So this is a completely general, very important class of control problems. Let me give you the most boring, unimportant control problem you can think of. Okay, so here's an M1. It's just basically people lining up in a bank. You've been to a bank. People come in, they get served, and then they leave. All right, and there's some service rate, and there's some arrival rate. You know, And there's whole big books on queues and trying to understand the delay in a queue, and when you have multiple servers, how they should be working, things like that. But what about the most boring problem in the world? Is a bank with a server. What's their optimal decision if you want to minimize the delay in the bank? That's pretty basic. And let me look at the most boring example of this. So Q of t is going to be the number of people waiting in the bank. And so the new number of people is the old number of people minus the number of people got served. And what's the notation I'm using here? Oh, I'm using t. Damn it, I was going to try to avoid that. I told myself I was going to stop using t for discrete time. I did it. But anyway, I'll try to do better. I would like to use n for discrete time and t for continuous time. That's going to be what I'm going to try to do in the future. So this is a particular model of a queue where u of t equals 1 means I'm working. And if it's 0, I'm idle. All right. And if I'm working, b of t plus 1 is the number of services that I've completed in time slot t plus 1, and a of t plus 1 is the number of arrivals at time t plus 1. Right? So this is like potential services. Now, in the MM1 queue, a of t, these guys are IID. What this is it's, so A of t is ID, the probability of an arrival, there's just one arrival at each time slot, one and none. So the probability of an arrival is alpha. Sorry. All right, so A of t in the M1 queue is either 1 or 0. And so alpha is the probability of success of an arrival, and 1 minus alpha is a probability of failure, no arrivals. And b of t is 1 minus a of t, which means that either, at each time slot, either there's a potential service completion or there's an arrival. All right? Where this comes from is taking a continuous time model. I'm not going to give you the details, with particular statistics for service and arrivals, and sample in a very special way the process to get a discrete time model. Okay, so I'm not going to get into that. You don't need it. This is just a Markov, controlled Markov model, as we've talked about, under the assumption that A is IID. And this restriction that A and B take on values 0, 1 is just simplifying. I don't need that. But you can see how it makes things simpler here, because I'm not clairvoyant. And if b of t plus 1 could take on values of 500, and I don't know that, what is u going to do? I mean, I can't serve more people that are there. So it makes it more complicated to describe policies and stuff. Okay, cool. So we have the same sort of thing, but it's really hard to work in discrete time. So remember before I said, what if the noise is 0? And I went through and solved the problem. I could do that here and just replace these guys by their means and have a discrete time system. It's much easier to go to continuous time. So I'm going to do two things. I'm going to look at the mean dynamics, and I'm also going to go through and look at continuous time. And the reason for doing that is this. I mean, so first of all, you all tell me, what's the optimal policy if I want to keep the Q length small? I'm not going to give you a cost function. You know what the goal is. I want to keep the Q lengths from getting big. Any cost function, which is, I've got my cost function, I don't care. It might be quadratic, it might be anything. I want to keep that, I want to keep the Q length small. What's the optimal policy?
It's 1.
What's that? It's 1. U star of t, I've started with t, equals 1, but only if q of t is positive, because otherwise I could go negative. Q lengths can't be negative. Okay, so q lengths are 0, 1, 2, 3, 4. And if q of t is 0, well, then I can't do anything. I just sit there and wait. Okay, so, but I want to, let's go and derive the equations and all of that. We have to think, let's look at an specific example. So the typical thing in operations research is to take C of x equals x. And the reason for that is it's related to waiting times. So if you just look at if you minimize the mean Q length, you end up minimizing the mean waiting time as well. So that's the reason. So there's a dynamic programming equation. The same Bellman equation is going to hold. It's simplified a bit because the cost doesn't depend on U. And we can try to solve this equation. And we can try to solve this sort of mean field model. But again, I'm going to do it in continuous time. And who knows, maybe that's been a mistake. Maybe I should have, it just looks so messy. If you replace this by its mean and this by its mean, you get this discrete time system. It's really ugly. Continuous time is really pretty. How about if I do one more line? What does it look like? Think about this for a bit. What is, if under this policy, what is the evolution of the stochastic process as time evolves? Here's t. Here's q star of t. And let's assume, let's make it big just for simplicity. Let's say that q star of 0, the number of guys in the bank, guys and gals, is 10,000. I picked that out of my hat. What's going to happen? Why did I pick a big number? It's because I want to say, well, at least 10,000 steps. I'm going to keep u equals 1.
It's a lot of people in the bank.
It's a lot of people in the bank, but my point is, I've got that policy, and it's going to take a lot of time for q star to be 0. That's the point. And so basically, that disappears, you know. And I've just got the new guy. All right, so under this policy, the new q, if I get an arrival, I go up by 1. If otherwise, I go down by 1, provided I can't go down. So it's going up or going down. And basically, I'd like the probability of going up to be smaller than the probability of going down. So let's make that assumption. Okay, so alpha is the probability of going up. 1 minus alpha is the probability of going down. And typically they denote this mu. So mu is the service rate. All right, so I go up, I go down, I go up, I go down, I go up and then I go down. And if I look at some large time block, I've got a proportion alpha of going up and a proportion 1 minus alpha of going down. All right? And so you've got a slope here of approximately I've got minus mu plus alpha. I mean, take a look at it. Look at the increments. That's the slope, all right? The mean increments. It's going to be the mean of this minus the mean of that. That's alpha minus mu. All right. So so this increment here is the noise into the system, and so forth. So anyway, this is the sort of thing I stared at back when I was a first-year professor at University of Illinois and a postdoc in Australia, and started thinking about fluid models for this, and basically saying, well, why look at a discrete model if it's sort of this boring piecewise linear behavior? Okay. Okay, so the fluid model. And I'm calling it a fluid model just because there's a long history in queuing theory of these fluid models, going back to the 70s, 60s, of looking at fluid models for queuing systems. And it's just the differential equation you'd expect, that Q dot is equal to that mean increment, alpha minus mu.